Yeah.
And you can grab me one?
Gotcha.
Oh, thanks, sir. Oh, I'm down. No, it's from Celsius to Kelvin. You're adding to it. They should.
I'm gonna walk out. I'm literally just gonna walk out and be like, calm down.
Probably like logo. Probably like logo and then turn around for game. Logo turn around for game. Not like in an East game. Like 5. Yeah, pick up 5. In a 1v1.
I got my dress.
Oh, I'm not in 5 seconds.
I like your headphones away, please.
Oh, this is the unit. I'm about to tweet. I am so serious. I'm like, spaz out, have a heart attack in the concert.
You actually wanted me to fix it. I just couldn't shoot.
Those are the things that you're missing.
So you was like, wait.
It was like 10
Is this the lab that we did?
Okay, so here we go, ladies and gentlemen. 52.3 Celsius. To go from Celsius to Kelvin, we add 273, ladies and gentlemen. That puts us at 325.3 Kelvin for your temperature. Questions? Good. Convert 246 Kelvin into Celsius. Kelvin into Celsius, we simply subtract 273, ladies and gentlemen. If we subtract 273 from that, you get a temperature of negative 27 degrees Celsius. All right? So that is what you should have gotten. On a test, I will give you this much information, ladies and gentlemen. I will ask you to convert from one unit of pressure to another, and I will give you the 4 standard pressures for you to be able to use to convert these. So, convert it, ladies and gentlemen. Let's go.
And then on the top, since we're converting the numbers, standard numbers. And then since there's only one bottom,
It actually doesn't understand at all.
What do you need, sir?
And it's like,
You did not dunk it, no.
right? So like someone.
Okay, well, you're in the unit of ATM, right? So, take and write that number down. Put a time sign and a fraction bar. And on the top of that bar, you put the unit that you are going into with its number. And on the bottom of that, you put the unit that you are in with its number out of these 4 right here. It's the molar conversion to 1-step molar conversion. Correct.
And then the bottom
The bottom is whatever units that you are in, because that's the only way you'll get it to cancel.
That like has a dress. Exactly. Literally exactly.
I know some of those. I just can't remember.
So
This number,
this number times your converting number.
And I'll just
Divided
say
by
here,
the-
that's what you
What time?
All right. So, ladies and gentlemen, my turn for a little bit, please. So we begin with the number that we are given, 2.13 ATM. We are going to do a unit conversion, which means we are going to multiply. Now, we need to be careful. This is unit conversion. We are going to multiply by a factor that has something on the top and something on the bottom that are equal to each other. Later on in this unit, we are going to set up proportions which will be equal to each other, which we will treat differently. But for right now, ladies and gentlemen, since ATM is the unit here, we take this one ATM and we put it on the bottom. We are trying to get to the unit of millimeters of mercury, so this 760 millimeters of mercury goes on the top, ladies and gentlemen. And now you simply do the mathematics. The mathematics say take 2.13 times the number on the top and divide by the number on the bottom. When you do that, ladies and gentlemen, you will get 1,620 mmHg. Now, you might have come up with a number that was slightly different than mine. I have rounded mine into 3 sig figs since the 2.13 was in 3 sig figs. So I have the 0 after the 2 because I don't want that spot here to be significant. And the 0 holds the value, but it does not add a sig fig to this number. Questions, ladies and gentlemen? Yes.
Behind you, what's the third thing that's on the quiz? Is it temperature conversion?
Yes.
Okay, thank you.
Okay. Last one. Here we go. Convert 87.5 kPa to PSI, ladies and gentlemen. That's what your problem should look like, ladies and gentlemen. Take the number that you are given times a fraction bar. You're putting something on the top and something on the bottom to get out of the unit that you are in of kPa and into the unit you want to be in of PSI.
So whatever it is in there. Going in the PSI.
I would round it up to 3.6, so just do it one.
Okay, what number's got to go on the top here, ladies and gentlemen?
14.7.
What number has to go on the bottom?
101.3 kPa.
Yes. These four numbers are what you use to make these fractions always. Okay? Always. The one that you are in is the one that goes on the bottom, 101.3 kPa. The one that you are going to, 14.7 PSI, is the one that goes on the top, ladies and gentlemen. When you set it up that way, you should end up with 12.7 PSI.
What was the answer for the last one?
The answer for the last one, 1,620 millimeters of mercury.
Okay.
Questions? Okay. All right. Now, yesterday, ladies and gentlemen, we were working on Boyle's Law. So, in your notes, ladies and gentlemen, you should get to slide number 23, please. Okay? Slide number 23. But we were also working on this. So let's go back to this. If you don't have the information, that is fine, ladies and gentlemen. But there was a problem with this yesterday, and when I looked at it with your class, I couldn't figure out what was wrong with my graphs, because the graphs were not coming out the way I had expected them to. So I looked at the graphs after class, and I found this. Google has made a little enhancement, ladies and gentlemen. Google has decided that the way you put your numbers into a table is the way they are going to display them. If you look at your graph for the first one, yours should be very different than mine. KP, you either need to stop or go. Those are the options, okay? Go somewhere else. But right now, you're stopping me, you're stopping the whole class, and I want to get through things to give you time to work on problems. So your graph looked very different than this yesterday, ladies and gentlemen, and then after class, I realized what it was. If you look at your numbers down at the bottom here, they are reversed. They start out with 55 and they go down to 25. Who would make a graph starting out at 55 and going down to 25? Well, apparently Google would, ladies and gentlemen. So when I put them now in the right order, which yours is not, when we look at this graph, what does this line show us? What two relationships does this line show us? Inverse. Why? Because the line is going down. Good. What's the second relationship? It's on your quiz tomorrow, so I really hope you get this. Why? It's not a straight line. Well, in science, we hate two things. We hate non-constants, and we hate inverse lines. So we are going to do a simple mathematical trick to this information to make it be what we want it to do. I am not expecting you to do this, but I'm telling you this is what I'm doing. And what I'm doing, ladies and gentlemen, is I'm going to take the inverse of pressure instead of pressure. Now, what does the inverse mean? Kind of the reciprocal of it. Thank you. So instead of using 106.46, I'm going to use 1 over 106.46. That is the numbers that I got here that I took the reciprocal of. So now we can see that as these numbers go down, these numbers also do what? Go down. That means it's a what kind of relationship? It's a direct. And again, now, when I switched my axis numbers around, which there's a button that you can do with Google that I didn't know there was a button you can do. Now look at the line that we get. What do we get? We get a direct relationship. But more important than a direct, we get a constant because the line is straight. And now because we get a constant, ladies and gentlemen, this becomes a very easy line to work with because any straight line in math can be found by what formula? Thank you. Y equals mx plus b. Y equals mx plus b. And the nice part is even in Google, ladies and gentlemen, it will give you the formula for y equals mx plus b. Now, what does the b represent in y equals mx plus b? What? Okay, the y-intercept, correct? When x is 0. We don't really care about this point very much, ladies and gentlemen. What we do care about is what is m? The slope. Now, the slope of a straight line is a what? The slope of a straight line is a constant. It is a number that does not change. Now, in our y equals mx plus b, what is representing y? What variable is on the y-axis? Now again, sorry, let me move this a little bit. Actually not pressure. It is what? 1 over pressure. It is 1 over pressure. So this line says 1 over pressure is equal to, now this is the number that we get, 0.000166 x. Now what actually is x? What's representing x? The volume. So I'm going to take out that x, and representing volume is v, correct? Okay. All right. So now I have a formula, okay? Plus the b here. The b, now this is 2.39. The e represents times 10, a scientific notation, to the -4. So that means that is 0.123239. Okay? Now, I'm going to do a little bit of math to this, ladies and gentlemen. Okay? I'm going to do a little bit of math. Number one, I am going to take and get P and V on the same side. So I'm going to multiply this side by P. I'm going to multiply this side by P. But I'm also going to take and get the thing, this number onto the other side. So I'm going to subtract 0.000239. What I do to one side, I'm going to do to the other. 0.00239. Okay? So P times 1 over P is what? 1. So negative 0.00239. Why is it negative? Because I'm taking it from one side and moving it over to the other. Plus 1 equals, now, P times 0.000166 V. Okay? I want to get P and V alone, so I'm going to divide this by 0.000166. This will get me P and V on one side. What I do to one side, I'm going to do to the other. Okay? Now, somebody have a calculator handy? Good. Take negative 0.00239 and add it to 1. And then divide it by 0.000166. And tell me what you get. 6,009.698. Now, to be honest, not really concerned what that number is. But what we are concerned with is the fact that now this line gives us a constant direct relationship. And that, ladies and gentlemen, is the constant for this gas that we were working with. The pressure times the volume when we hold the temperature and amount of gas constant. And that is what Boyle's law is. In other words, we could take any 2 points on this line that we want. And if we multiply their pressure times their volume, this is the number that we are going to get. But it also means that I could go to a point that could be somewhere over here. And I could predict what the new volume would be of that pressure. That is what Boyle's law allows us to do. Yes, here is a small section of a graph for a gas, but we could expand it as far as we want to in either direction. And if you ask what would be the new pressure, all you have to do is tell it what the new volume is. Or you could ask, what volume would it be if the gas got to this pressure? That is what Boyle's law is all about. Being able to figure out what the pressure of a gas would be if we change its volume, or what the volume of a gas would be if we change its pressure. Questions? Now, all of this is just to show you that pressure times volume equals a constant. This is just the background for it. This is just the mathematics of it. Not going to ask you to do this on a quiz. I'm not going to ask you to do this on a test. But I am going to ask you to take this and be able to use that. And that's what we're going to go to right now, ladies and gentlemen. That's what we are going to go to right now. So, ladies and gentlemen, I'm going to take and get rid of this. We're going to go into here and let's talk about Boyle's law. Now, first of all, in words, Boyle's law is the pressure of a gas will vary inversely proportionally to its volume at a constant temperature. The one thing they don't mention in there is what is also constant. The amount of gas. In our first three gas laws, Boyle's, Charles, and Guy-Lussac's, they do not talk about it, but they always hold the amount of gas constant as well. Okay? Now, what that means is that P and V are in an inverse relationship. Okay? An inverse relationship where one is going up, the other is going down. But it also means that temperature and amount of gas need to be held constant. You can't go messing with those. You cannot go and mess with those. Once you have them set, you have them set, which is why we put the syringe onto the gas sensor. You could not change the amount of gas in your syringe yesterday. And we didn't heat it up or cool it down. So P times V equals K. Pressure times volume equals some constant. What that means, again, P stands for pressure, V volume. You will see us use a little k to represent a constant. Okay? It's a number that does not change. So what that means is that if P1 times V1 equals K and P2 times V2 equals the same K, we could set them equal to each other. Now this is what I was talking about a minute ago. These two are equal to these two. This is not unit conversion. This is not times a fraction. This is a gas law. These two numbers multiplied together equals these two numbers multiplied together. Now, I do not care what unit you use for pressure. I do not care what unit you use for volume yet. What I care is that whatever the pressure is here, this needs to be in the same unit. Same unit. Whatever the volume is in here, this needs to be in the same unit. You cannot mix milliliters and liters. You cannot do that. You cannot mix ATM and PSI. It will not work out. You have to be in the same unit for pressure on both sides. You have to be in the same unit for volume. Questions? Okay, skip that. A sample of helium gas in a balloon has a pressure of 240 kPa in a 1.4 liter container. What does 1.4 liter tell you? How do you know? Good. Units help you recognize what that number is. Now, I told you the pressure was 240 kPa. It didn't tell you what 1.4 liter meant. That is where you need to understand what the units represent. Liters represents volume. What will be the new pressure if the gas sample is transferred to a 3.0 liter container? Assuming no change in temperature, and also, even though it does not say it, assuming no change in the amount of gas. So now we are going to set up a Boyle's law problem. We are going to use P1 times V1 is equal to P2 times V2. Now, I don't care which conditions you call P1 and V1. Doesn't matter. But these two things go together. It's saying this is the pressure, this is the volume. They have to go either here or here. It doesn't matter which side. But they have to go together. So I'm going to take it, I'm going to put them here and here. I don't know what the new pressure is, but I do know what the new volume is. Now, before we go any further, what's happening to volume here? From 1.4 to 3.0. It's going up. What's going to happen to pressure? It's got to go down. So I don't know what the final number is yet, but it better be less than 240 kPa. Otherwise, you've done something wrong. So now this is simply a math problem, ladies and gentlemen. This is a math problem where we need to do what to this? Okay, can you explain a little bit more? Because that's not the terminology I would use. So can you explain what we're going to do?
Subtract 1.4 liters to the 3 point whatever, and then subtract the other two.
Nope, we're not subtracting here. Because these numbers are multiplied, and because these numbers are multiplied, we're going to divide this side by 3.0. It's okay. I would, in my day, we called this isolating a variable. I'm getting this number alone on one side because it is and it's not actually a number yet. I'm getting this variable alone on one side so I can solve for it. So I'm going to take and I'm going to divide this side by 3.0. What I do to one side, I do to the other. I get 110 kPa. Okay? I get 110 kPa. By the way, it didn't show you that I was doing this. Let me show it to you. I took this side and divided by 3.0 liters. That got rid of this and this. What you do to one side of an equation, you have to do to the other to keep it equal. Liters and liters cancel out here. Take 240 times 1.4 divided by 3.0. Now, it probably didn't come out to 110. It probably came out to a different number. How many sig figs here? Nope. 2. How many sig figs here? So my answer can only have 2 sig figs. That's the 110. The 0 is not significant because there is no decimal afterwards. Questions, ladies and gentlemen? Olivia, can you tell me what we actually got? Did you actually do the math? What was the number that we came up with? 112. Okay. Unit is kPa. Now to do 2 sig figs, the 1 is the second sig fig here. This one, the second one. So I need 1, but I need to hold the place of the 2 without it being significant. So we put a 0 in there. That means that I didn't take the number 112 and make it 11. I made it 110. Okay? I made it 110. Questions? Anyone need more time with this up there? The volume of a gas at 99.0 kPa is 300.0 milliliters. What is this?
Pressure?
Why?
kPa?
Very good. Didn't tell you that directly, but by knowing the unit and knowing that kPa is a pressure unit, you know that this is for pressure. How many sig figs? 3. The 0 is significant because the decimal. What is this? Volume. Why? Because it's in milliliters. How many sig figs? 4. Now, if you do this work ahead of time, it's going to make your life easier. Okay? If the pressure is increased to 188 kPa, what will be the new volume? Assuming no change in temperature, and also, even though it doesn't say it, assuming no change in amount of gas. We're going to, for now, assume no change in amount of gas. Okay? Unless it directly tells us there is a change, we're going to assume no change in amount of gas. Okay? So now, ladies and gentlemen, again, P1 V1 equals P2 V2. These two are together, correct? This pressure at this volume. Pick a side. They got to go to one side or the other. I'm going to put them on this side. On the other side, I'm going to put the new pressure that I get, and then I'm solving for V2. I'm solving for the volume. I'm putting the unit in there. You don't have to right away, but you do have to put a V there that we're solving for. Okay? And actually, that's the wrong unit. Why? Because it's got to be milliliters, because it has to be the same unit on each side. KPAs are the same, milliliters are the same. Now, maybe in the end, I ask you to give me your answer in liters instead of milliliters. We could do that afterwards. We've been doing that before, right? Still 1,000 milliliters equals 1 liter. And again, you don't have to show me how you do that calculation. You just have to do it. Okay? So, what do we do here? We divide both sides by 188. By the way, what's happening to pressure? It's going up. So what's going to happen to volume? Before you ever do the problem, because we know it is in an inverse relationship, we should have an idea of what our final answer should be. By the way, look a little closer. What happened to your pressure? I know it's going up. It doubled. Guess what happens to your volume? Should have. No, it's not double. Oh my gosh, I'm sorry. Thank you very much. It's not double. Good catch. Your math is better than mine today. It's yeah, it's not. I don't know if I originally wanted it to double, but it didn't double. Sorry, my bad. My bad. Okay? But it almost doubled, which means our volume almost went down to half. Again, that part about numbers and kind of understanding, my bad on that. I'm totally sorry on that one, ladies and gentlemen. We divide both sides by 188 kPa. kPa and kPa still cancel here. Milliliters is the only unit that I am left with. I am still letting units help me with these problems. Just like we did in the last unit that we were doing. You want to get rid of grams? Grams has to be on the bottom. Okay? When we divide this by kPa, we're dividing this by kPa. They still cancel out. Questions? Air is trapped in a cylinder fitted with a piston, occupies 145.7 milliliters at 1.08 atmosphere pressure. 145.7 milliliters. What is this? Volume. 1.08 atmospheres. Pressure. Yes, it's a gas, but it's the pressure of the gas. Okay? What is the new volume of air when the pressure is increased to 1.43 atmosphere? By applying a force to the piston, assuming no change in temperature. Okay? So, what's happening to our pressure here? Going up. What's going to happen to our volume? It's got to go down. It's got to go down. Now, stop for a minute and let's think about this. Remember the first day we started this unit? The Pong game. A ball hits this wall representing a particle of gas. It bounces off, it goes over and it hits this wall over here. And then it bounces back and hits that wall. Right? It does that once a second. Pressure is how often that ball hits the walls of the container. So now what I've done is it takes 1 second to travel from here over to there and hit that wall, 1 second to travel back and hit that wall, and it just bounces back and forth all day long. Hitting a wall once every second. This problem says I want that ball to hit the wall more often. I want pressure to go up. Now I cannot change its speed. That would be temperature. So what is the only way I can make that ball hit the wall more often than once every second? What is the only other thing I can change? Nope, can't change the amount of gas. Good answer, but we can't change the amount of gas. That's not an option, and we can't change how fast it's moving. So I have to change the volume. So the volume, this wall either has to get closer or further away. If I push this wall further away, what happens to the amount of time it takes to get from there to this wall if it's further away? Takes a longer time, which means, is it hitting the wall more or less often? Less. Pressure is going to go down. So the only way I can make pressure go up is to take this wall and move it closer. Because now it doesn't need to take a second to travel that distance to hit the wall. Now it will hit the wall more often because the walls are closer together. Now I hope, ladies and gentlemen, that you can visualize that, because one of the difficult things in chemistry is we talk about a lot of things that we cannot see. We won't see gas particles hitting the walls. Now you want to take physics, you want to learn about acceleration and mass and velocity, we'll put Farhan on a skateboard and we will shove him and we will measure how hard we shove him. And then we will measure how fast he goes, and we can see all of that. You can't do that in chemistry. We can't do it in chemistry. So I'm trying to help you by giving you a visual. Okay, still using the same gas law. Okay, still using the same gas law. By the way, I won't give you this gas law. I mean, you need to know it. You need to be able to say, okay, it's P1 V1 equals P2 V2. That it's Boyle's law. Now, hang on. It's not on the quiz this week. And before we get to a quiz where we will, I will hopefully summarize this and other gas laws for you. So don't go crazy yet. Okay? We plug our numbers in. Here's our pressure. Here's our volume. Here's our new pressure. Again, I'm a wonderful person at cutting and pasting, which means I still have the wrong unit here because I had the wrong unit on the last one, right? Don't roll your eyes at me. That's my wife's job, not yours. Stop it. Okay? So now, ladies and gentlemen, again, the only thing I need here is a V. Okay? But this is going to come out in milliliters. We're going to take and we're going to divide both sides by 101.43 atmospheres.
Sorry.
The formatting went away. That was 10 to the second. That was 10 to the second. Okay? Should have been 10 to the second. Okay? So, again, two different ways of writing it. I could have also wrote it as 110 with a decimal after it. That was supposed to be 10 to the second. I have no idea what's happened to my formatting here, ladies and gentlemen. Hold on. I know. You'd think I would have this all figured out. My last class didn't catch it last trimester. It's their fault. We'll blame them.
It's 22. Yeah. 36.
Okay, there you go. Questions?
Do we have to have it in the top?
No check.
No, you could have written 110 with the decimal after it. Okay? Two ways to actually express that number. 110 with the decimal after it, or you could have written 1 or 1.10 times 10 to the second. Either way. Okay? Yes. All right, ladies and gentlemen, the first page of the packet that I gave you has all Boyle's Law problems on it. Get with a partner, get to work on it. You want to go back, work at the lab stations, you are welcome to. You want to work at it at your desk, you are welcome to. But there are 4 problems there for you to practice, ladies and gentlemen.
Is there any problems for the quiz tomorrow?
What?
Is there any problems that we
Boyle's Law is not on the quiz tomorrow, no.
So there's nothing we can do to study for the quiz?
Well, you can look over your notes on how to convert pressure. You can write a pressure down in Celsius and convert it to Kelvin. You can write a pressure down in temperature down in Kelvin and convert it to pressure. You can take these pressures and convert them into other units if you would like.